some really exciting things today, all about texture mapping and applications. Before that, questions? Homework 5.
So once you have the camera behind the mirror so it shows things, how do you figure out exactly how do you like cut the texture down to the right size and shape?
Well, there are various techniques. The techniques that I thought that academically make sense to practice is to say that I'll create triangles and using texture, we'll discuss today, we'll map triangles to triangles. The moment that I specified 3 points, the linear interpolation will map them into 3 points. And we'll hand all the homography that we'll also talk about today. That was if you want to assume that the camera is arbitrary, and then you're getting some bonus points. Then comes the simpler assumption that the center of the camera is behind the mirror, and then you can play with the simplest solution is either the angle of view or the specified the postrum that you specified by near, far, and so on. So essentially, you can generate, if you're willing to take points. Let's talk about it right after this topic, because I think that it answers. So the big answer is that you don't mind making error in the sense of taking the field of view too large, the field of view of the camera behind the mirror. You don't mind that it will be too large, and you don't mind even that there is some distortion there, as long as it contains the real image that you want to show. And then how do you pick it, the real image, to place it on the mirror? It's texture mapping, the way we do right now. But there are ways to make it simpler than what I just said.
So for the most part, you put the UVs, then you set that in the texture or in the model?
Wait 10 minutes with this question. I'm answering exactly it in this question. That essentially, I want to, here is a triangle which is in my model. Here is an image that I want to map from this triangle into this triangle as a texture. Take a piece that is, in particular, takes this vertex to this one, this to this to this, so that all the details in between will be interpolated into details on this triangle in a reasonable sense. Why is this relevant to homework 5? Because if you want a bonus point and you said the camera behind the image is arbitrary, is in some arbitrary location, that is, here is a wall, this part is a mirror, here is my eye, and I'll actually take an image that is taking too much of what the mirror sees. That is, you also see a piece of the wall if you care. Actually, you don't care. That's just a piece of the object here. You don't bother. Eliminate as long as I know what are the, in 2D it will be 2 points, in 3D it will be 4 points, 2 triangles, which point matches to which other point. At the simplest, you can say, you know what, if the camera is, even if the camera field of view supersedes the side of the mirror, I don't care. I just assign these 3 points, 4 points. In the image that I produced by the Z buffer, by the rasterization part, from the camera on the wrong side of the mirror. Something about you. You don't look like I answered.
I just don't know how to do that in WebGL because there's a bunch of stuff we've never really learned. So.
how do I find these points? I showed it last meeting. And there is a GeoGebra that does all the math that you can cut and paste if the camera is outside, you're saying. Here is my big image. I ignore the effect of the wall completely. I'll ignore the effect of the wall completely, but essentially what I take from everything that the I prime is a reflection of the I in the wall, from everything that the I prime sees, and I don't care very much even about the direction of I prime, as long as it contains the four corners of the mirror. How do I find the four corners of the mirror? Think about the foursome of everything that you see, and does just solve ray shooting. It's just the same as ray shooting. We can discuss it more after the class if you want.
All right.
But once I found these 4 points, my problem is solved, because then I'm just saying I'll handle the map, the texture mapping, handle everything for me. Now, a bit more about the texture. We want to represent everything in coordinates u and v. For every triangle, we would like to have 2 parameters, u and v, such that a piece of texture will match nicely a piece of the image that we show, that to start with. And what we are doing with the texture very commonly is putting patches next to each other, which is not a big deal if we are just mapping it, repeating the same patch multiple times. Not a huge deal. You hopefully did it in homework 4, of just repeating the same tiling multiple times, the very same image multiple times. And on a flat surface, it's still, there still could be quite some issues, but they are not as scary as on non-flat surfaces, that these tiles might touch and deform in all kinds of strange way. But here is a motivation. Why? What can we do with the texture? With texture mapping. We will see, probably not today, how we can use it to create shadows. There is plenty of other very cool applications. There is a bit boring math that I'll go through, but then we are going into very cool applications waiting for us. Okay, like how do I create such dramatic images out there? And the question is, do I actually have the very latest version of this file? Take a look up. Yeah, it's okay. So, yeah. So I'd like, as I try to enforce from homework 1, we'd like to have everything with coordinates u and v, since we are in 2D surfaces, coordinates u and v, and everything that we care for, everything in the triangle, is parameterized by these 2 coordinates, u and v. And that's all we need when we have not necessarily planar, but at least manifolds that are 2-dimensional. 2 parameters are enough. And I'll show a few very simple examples coming up into it. What are these functions that we need? So we can think about it as a function phi that look at the surface as for the surface, and for every point on the surface, it will be less abstract in a second. Every point on the surface match a point of the texture. For every point in 3D, match a point on the, as for the surface, some 2 coordinates uv that will be in the texture that you want to put on the surface. This texture can be an image of the carpet. It might have repetition or might have not. And it could be much more exciting than just a picture of the image. But play with it. But, when I have to create a texture, I want to know what are the number of coordinates and so on. Once I have one particular point, I will get the normals. How do I get a normal? Well, maybe I'll assume that the normal is just a normal to the triangle, we'll see more exciting options today that go through the texture. What are these normals? I will get the texture for this particular point and use this normal and the piece of the texture that I just brought for this particular point. And this particular point of the surface, I don't care one bit if I got to this point via Z buffer, rastering operations, and the pixel level, or it's done via ray shooting, all the same. Same. Thinking about it the same way, create the shadows, shading at this point, and voila, you can answer what happened to this point. A bit boring math. How do I decide what is this mapping? Let's start from triangles. I want to take a triangle that you see in 2D, triangle in your scene, and map it into triangle of the image. For example, you created the image of the mirror, and now, and that's part of the math that you don't have to worry about deliberately once you use WebGL. You just let each pixel just interpolate linearly, bilinearly. But let's still understand how it works. So what stands behind all the linear interpolation is always the barycentric coordinates. Also, the same result we would get via the bilinear interpolation, which means what? Well, first I'll represent every point P as a linear combination of the three vertices. I need it as a way to get representation using U and V, as before. I want just two parameters to coordinate 2 points for every. So if I want to give weights to A, B, and C, how do I do it? I think that it's the first time in the course that we are going through it. The weight that B is getting is the area of the triangle. I mean, I want to ask what is the weight that the vertex B is getting when I create an attribute of a point P. How do I do it? P is a point on the triangle, and I need this weight. And I want to use these weights, WA, WB, WC, to interpolate the locations of A, B, and C. That will be just a linear interpolation. But the same weights, the very, very same weights, I'll also use to interpolate when I'm picking a point from the texture, just the colors, RGB, or other properties that I want to interpolate between them. So the weight that the point B, that's how B looks like, point B is getting is, for the point P, look at the area of the triangle that is not adjacent to B, divided by the area of this whole triangle. And we are doing it for all the three vertices, and now what is P is the weight that we gave to A times the location of A, plus the weight that we give to B, plus the weight that we give to C, and as you all know very well, this is a convex combination of the three weights. Why? They sum up to 1, and they are all positive. So why is this cool? I can also represent it as, let's write this point P as, I'll compute the weight of B, the blue triangle, the weight or the area of the blue triangle. That would be the weight of B, the area of the blue triangle, divided by the area of this whole triangle ABC. We start. I have a point P on the triangle ABC. I want to compute what are the barycentric coordinates of the point P, which means to present P, you want to give weights WA, WB, WC to each one of the points. And as before, the weight of the point C would be the area of the triangle not adjacent to C divided by the area of the whole triangle before. But now I want to write it in slightly different way. Instead of giving some way to A, some way to B, some way to C, I'll write it in the following way. A plus W of A, W of B Yeah. Okay, so only the latex was wrong. The math, okay. The weight of B times B minus A plus the weight of C times C minus A. That's how I created the point P. So far it looks completely pointless. Why do I need to represent P? If I know P, why do I need to represent P as a linear combination of the other points? Well, maybe I want to generate all the points inside the triangle given the location of the vertices, ABC. Maybe I know, in addition to ABC, the location of P, and I want to interpolate other values that are not just the location, like the color, or in the case of the mapping, that somebody told me, I want to take the image, and the image that you see from the camera, that exactly answers your question, the image that you see with the camera is much larger. But inside the image that I noticed in the camera, I decided to map the point A prime, point in the image, to a vertex V of one of the triangles in my texture. But in my scene, C prime will be matched to C, B prime will be matched to B, and voila. Using this barycentric coordinates, I can now define a new point, P prime. What's the location of P prime? It would be A prime plus WB. WB is what I took from here, times the analogous from here, B prime minus A prime, plus W of C, C prime minus A prime. What's cool about it is that now, if I move P wanders around this triangle, the point P prime that lives inside the image, I'm going to the point P prime and fetch the RGB value of the image at this point, what the virtual camera saw in this point. I'll take the RGB from this point and copy it to this point. And this barycentric coordinate linear interpolation actually behaves exactly the way you behave. When P is on A, you're watching a point which is near A prime. You'll take the color from the image from P prime and copy it to P. If your point is on the midway between A and B, then the weights would be accordingly. The weight of B will be much larger. The weight of B will be much larger than the weight of C, and accordingly, P prime I will fetch. I will copy the RGB from here and copy it to here. So I made this GeoGebra just to show you that barycentric coordinates is what works under the hood and generates, Okay. So just to show the moment that I wrote the triangle as A plus, what is this number that I wrote over here? In the GeoGebra, let's note this number. What I wrote as WB times A minus B, that's one of the coordinates. Let's call it U. It's between 0 and 1, always. W of B will be between 0 and 1. Same goes for W of C. No W of A, so they'll sum up to 1. And that's all I need. Yeah?
Is this equation the same as this weight A,
Yeah. In vector coordinates, it would say go all the way to A, and then add some walk in what direction? In the direction of this vector. Go to this vector by some amount, and then from wherever you're reaching, go in the direction of C minus A, this vector, some amount, into the interior of the triangle. But yes, this is because the weight, what's written here when you think about what it's W, because 1 minus W of B minus W of C, again, 1 minus this creature. And this creature leaves me exactly with the weight of A. So yes, it's a cute little trick that gives me the U and V that I needed. This slide just repeated 17 times. And now I can do tiling. Like I can map half a triangle to half a triangle. So far, there is no homography, no parallax involved. We'll talk about it. One triangle to another triangle in this part, and I can do it modulo the size. When I get to some number larger than 1, I'll just do modulo 1, reduce 1. And that's where you copy one tile to the next tile, to the next tile. So far, there is no much problems in this case. Question what happened at the end, so on. Back to the GeoGebra for a moment. Notice that I'm copying the image to the text, and I don't care at all how these two triangles, it will be a linear aberration. These two triangles don't have to be similar in any way or shape. They just need to be triangles. Makes sense? The moment that I decided which vertex match to which other vertex, it's a done deal. Actually, the moment that I decided about one vertex, given that they are both counterclockwise, it's game over for every other point in the triangle itself. So it's fine if my eye watches the mirror from one direction and the camera actually watching it from completely different direction. You don't need to worry about this transformation. Generate the image that the camera sees when it stands behind the wall, in the virtual camera that it stands behind the wall, pick the right points inside it, and map the vertices to the vertices of the mirror. Getting overly excited about this topic, obviously. So far, no problems with the matching. Let's talk about slightly more interesting texture mapping. You are taking a I want to map the texture consists of the multiplication text, them in a cylinder, and I'll use two parameters, U and V, as before. U and V are U and V will be coordinates of the image. So I'll assume that the image goes from U between 0 and 1 and V between 0 and 1. And now I need to compute U and V for every point on the cylinder. Right? And what do I want it to look like? It's just like taking the cylinder, and now here is the image, and wrap the image around the cylinder. Nothing fancy. Right? Take the image and wrap it around the cylinder. How would it look to you? How do I map a point on the image that you see on this white paper to pixel in the RGB? And the answer is that's how you're using the U and V, at least for a cylinder that Z right now is a height. Let's understand this formula. I think that we'll understand. So I'll use first the different transformation that takes U and V that will be parameters that I'll decide on and maps them into points on the cylinder itself. So V will be nothing but U will be the height on the cylinder. You can see there is a circle that moves up and down the cylinder. I'll decide about the lowest point of the cylinder, the highest point of the cylinder, and this is just a Z value. V is just a Z value, except that I normalize it because the cylinder is limited, so I want the lower part of the image to be aligned with the lowest point of the cylinder, highest to highest, and between 0 and 1. So the height is just normalized by U and V. Height is between 0 and 1. What about V? V will tell me how I move along the circle. Okay, so V0 now moves between 0 and 1, meaning I'm doing a full rotation around the cylinder. V will tell me if I'm, V is the one that tells me where I am around the cylinder. So what are it will be louder than one. Here is alpha. Alpha is nothing but V, except that V needs to be between 0 and 1, so I normalize it to be between 0 and 360 or 2 pi, whichever you want to work with. And now, if I gave you alpha or V, you can compute on which point x, y, and z it will appear on the cylinder. Again, if I'll tell you what is this angle alpha and what is V, how high I am, what is V, how high I am in the cylinder, you can ask where it is, at which point x, y, and z. So I can also do the reverse. Do ray shooting, ray tracing, or use a Z buffer and you decide that this is one of the points that you want to assign color to, and you want to ask where should I go to the image to fetch this point. What should I do? I'll take x, y somewhere on the cylinder. Now I take a cut. Deciding where do I cut it is just the z value. So from now on, it's 2D dimensional. What do I need? How do I map it in the u direction? I need to know what is alpha, either this way or this way. What is alpha? Alpha is what is the y divided by the x. Again, the y divided by the x, that's tangent alpha. But this divided by this is tangent alpha. Doesn't matter if alpha is clockwise or counterclockwise. That is, if you gave me alpha, I know to generate x and y. And if you gave me x and y, then to find alpha, I need to do arctangents. Arctangents or tangents of -1 of y over x. Okay, and then it's just the question of when do I start it? I added pi here just to say that when I'm looking at the triangle directly, that will be would be the closest point to the y. Make sense? So that's an example of computing nonlinear parameters, such as computing an image on a non-planar object. Smooth object, very simple object cylinder, but can I do it with, yeah.
Physically, why is it arctangent to? Is it squared?
No, it's just that's the GS code to do it.
Oh, that's like the
Yeah,
okay.
that's just a text for it. It's just tangents. And the division by 2 pi is just so to normalize it to be between 0 and 1. So as I am walking around the cylinder, when it's nearest to you from the viewpoint, it will start from alpha equals 0 all the way to 360, which brings us to right here. Okay. Can traditional Z-buffer algorithm may take a triangle and make it look like it's a bottle that appears right here, given that I told you the image and I told you what is the transformation. Can I just generate it using the Z-buffer algorithm? Not really. There are other objects that hide it. So not really. Z-buffer by itself cannot do it, but luckily enough, we moved, or hardware moved enough, from the late 90s, and now the buffer is replaced by shaders programming, and you can definitely ask every pixel. Here is the map that will tell you, and it doesn't need to be a linear transformation. Here is a map that will tell you for these particular coordinates, x and y, go and look to this point in the image. And you'll use it in homework 6 when you'll do some kind of Snell law, basically reflection and refraction of light in a surface of the pool. Similar, now it's a map, a globe, sphere. What would be, again, I need a coordinate, I need to map it. So for given x, y, and z, I can figure out what are the u and v. Where does it appear in the image? Well, presumably you have all discovered it in geography lessons. X, y, and z. R is fixed, is not one of the parameters, and u and v are nothing but the longitude and latitude. But you're just asking at which angle you're rotating now in one direction. That would be the first arc tangent, and to get the other coordinate. It's actually arc cosine, asymmetry. Okay. And what's the problems with finding a good phi? That sometimes it works, but sometimes, especially when I do the styling, it doesn't really match. But I want neighboring textures to have roughly the same area. If they are neighboring, they cannot be, looks like they are very different area of these textures. So, and I want at the same time to have the angles respecting the angles of the surface. I don't want a distortion that would mean that one edge of the texture would be much shorter than the other one, giving that they are neighboring each other. So this function is quite tricky to find. And there can definitely be bad things that happens when I create texture of surfaces, anything that is not as simple as triangle, quad, and so on. So size distortions, scales, textures kept to constant across the surfaces. If it's nearby, they should not look like one tile is very different than the other, and not too much distortion of the angles. Now, do you have distortion in the angles in homework 5? Do you have distortion in the angles when you're mapping an image to an image of the plane? Absolutely. You have distortion of the image the moment that you have any homography, parallelization, parallax. Right? The moment that you take this image of this rectangle when it's standing closer to you, the way that it will appear on your screen, the way that the mirror will appear in homework 2, would be if is not just in front of the center of the mirror, one side will be closer to the other one, which is absolutely fine. And you don't need to worry about it because it's still an affine transformation. Becoming a linear transformation in homogeneous coordinates, becoming just linear transformation as much as we know, assigning a corner, 3 corners to 3 corners of where it appears in your final image, and it just happens automatically. Just to explain what are this discontinuity and changing of angles, right? We want to map the multiplication table into this. I need help. It has a name. Exactly. Whatever. This polytope, we want to map the surface to the polytope and keep what's neighboring here, and keep the angles the same, and tricky. Okay. You'll see, like quite obvious over here. The 2 does not continue naturally. The 16 does not continue naturally to whatever is to the 26 that appears right here, right? Completely chopped. So once upon a time, there was only texture of images to images, and then people said, hey, we have hardware that can map triangles to triangles, let's map more properties, like transparency. It's a planar object. I just assigned all the pixels that are not on the object to be transparent. So you can see things behind it. That would be one thing. So what I did is that for the very same triangle, the same one single triangle of the mesh that you are going to show, there is plenty of different maps that you can map to it, and each one can say different things. And again, the part of I'll provide the image. For example, I'll provide a black and white image that will say for every point, is this transparent or is this opaque? And the rasterization, the gizmos behind the screen will map the points of the triangles that I need into points here, fetch the coordinates, and then I can make whatever I want from this number, like assign it as the alpha value. Okay, and I can also take parameters like for every individual. I still didn't tell you why I want to do it, but I can map in the same way my input image will contain the specular and diffuse coefficient, KD and KS. Why? You'll see in a second. What's the advantage of it? Other things. If I have this nice lake and mountains in the background, they don't change much, even in interactive games. What is far away change much in terms of perspective. It will change, of course, when you rotate. The parts, if the camera changes its direction, it does change. Zoom in, zoom out does change. But these are all operations that I can do on the texture mapping automatically by just assigning different pieces that the viewer actually sees. But I can tell WebGL, this is my environmental map, cube mapping. I'll give it the 6 images that will contain the walls and floor and ceiling. And why can I do it? Because to make one tree somewhere in the background occludes another tree, I need to move quite a lot, and anyhow, it's so far in the background that probably I don't see it. So because it's far away, even if you're moving, the image is fine modulo the homography, of course. If you are changing your location, you need to do something for the image. If I look at the same image, but now my camera is right here, then obviously this part should be larger than this part. But that happens automatically when you assign the camera parameters. More impressive example of the environmental map, cube map, that's what you're providing. Right? An image of the 6 images, and it is basically texture mapping or images that you put far, far away in the infinity. Okay. And how do I do, say, ray tracing with it? If your ray hits a surface, then you're returning what's a surface. Surface like one of the triangles. You're shooting a ray. My ray hits a surface. Well, then I do the normal things of returning the value of the surface. But if my ray did not hit a surface, my ray goes all the way to infinity, then instead of just returning a null value, the background is always dark or something, return the value that you're getting from the sphere maps. And these are functions that are built in WebGL, OpenGL actually. More exciting. I can give a new image that the values will not be colors at all. The values that I'll give will be, could be the direction of a normal at this point. I'll decide that even though it's still a triangle, and I'll treat it as a triangle when I think about, hey, is this triangle occludes or does not include on which pixel? It occludes another triangle for hidden surfaces removal, depth calculation. I'll treat them as planar simple triangles. But when I'll get to the issue of actually rendering them, I'll pretend that actually there are normals involved with each point. And for every pixel, what is this normal? It's not the real normal to the triangle, or it's the normal to the triangle deformed or changed by values that I'll give as RGB of the surface at this point. And there are a few variants that are different. I can specify the angles of the normal for every pixel, different for every pixel. I can specify some deformation that I'll do to the surface going up and down, from which I can compute these deformations, compute the normals, and I can use even this height deformation in a more sophisticated way that we'll see in a second, that will give even more dramatic effect. So once again, here is the normals of the surface without all the deformations. And now I can start pretending that there are normals given as a texture, or normals given as height, or even that the height are significant enough to introduce more changes. Yes?
So is the actual surface that, like, ridge on the top, would that affect occlusion in certain situations? If you have, like, two triangles and one of them juts?
Sometimes yes, sometimes no. It's up to you. When normal map and bump map not, relief map, you could. Usually you don't have to, but sometimes. Let's go to the relief map. And so why do I want to do it? What's the advantage? Why wouldn't I want to keep everything the same? First, let's see some examples. Orange. I want to give it a rough surface look. How can I do it? I'll say it's still a sphere. For any hidden surfaces removal, computing the depth, there are other objects that occludes the orange, nevertheless. So I treat it as a sphere for ray tracing purposes. But when I would decide about the actual color that I'll assign to each pixel, I'll say, hey, there is some shading involved that depends on the normals. And the big question is why? Why should I give this normal business instead of telling you a mesh of triangles that captures the surface? And there are a few good reasons. What's the advantage of it versus just giving you the surface of the orange explicitly as a triangular mesh? Many, many triangles. OK, so I replace every triangle by one pixel. So I saved, instead of a triangle or a vertex of the triangle, it's one pixel of the texture. So that by itself is a saving of information, but not tons of. But I mean, there are two extremes here. I can tell you just the image of the orange, as you all see it, give you the exact image with all the shading involved. That would be one extreme, whole image pre-computed with the normals. And on the other extreme, I'll give you the full 3D surface of the texture. So in terms of information, what did I save by assigning this bump map? Pixel is less than a vertex, but by a lot, but it's still constant change. So that's not a huge save.
Theoretically, couldn't you have like a partial bump map if you wanted the same thing?
Fantastic. What do I need to, how much information do I need to give you so you can generate this ceiling with all the holes also, or the floor with a carpet, right? They are all changes, but it repeats multiple times. But I can give you the bump map of only a small part of the orange, and you'll tile it multiple times around the orange. Great, but then, so okay, so I saved information comparing to the whole 3D map. But then, what about the other extreme? Why shouldn't I give you the whole image originally with all its, in all the details? You see it already. What did they save by giving you, or what did they obtain? It's not saved. What did they obtain by giving you?
You actually know the normals at each point for shading reasons?
But I can give you the original image of the orange already with a shadow built in. Exactly this image.
The shadows built in, you can't dynamically do the lighting as easily.
People, you don't play enough computer games. You're not static in the scene. The whole thing is changing, the scene is changing. If I'll give you just one portion of the orange, it will look different here and here. But because if I'll give you a portion of the orange, it will look the same at this part facing the light or the part on the equator. And if I'll give you the full image, it will not change when I'm changing my location. Just a few more examples. Like I'll give you the moon and the bump map of the moon golf ball, or the bump maps over here that will give you all the maps. And once I'm using this bump map, once I know the direction of the light, I can decide for every pixel giving you direction of the light. Are you facing the light or are you not facing the light? Are you expressing, given the location of the light and the location of the viewer, specular effects over here? Make sense? But it doesn't, so it's just a nice comparison between, it stands between full 3D mesh on one extreme, just a static image that don't change at all, and look how cool it is. From Wikipedia. The light is changing its location, the light changing its location, the triangle, it's one plane, it's two triangles that you see over here. Just only one single image, supposedly, but I'm not entirely sure. A bit suspicious here. But at least small changes, the effect of the light are very noticeable. And you can get very close to it by just this playing with normals of each and every individual point, at least for small changes. Where are you using the normals? For every pixel, do its own shading individually. Facing the light does not face the light, depending on which direction you're changing it. Okay, so that was changing the normals. So we mentioned we want the normals in one way or another, relief map, bump map, relief map, one of the two. Because on one hand, we can tile it, repeat it multiple times, and still make it change the location of the surface, and still make it reacting to changing of viewer position and or lighting position. More examples where we are using similar texture. Here is a nice image, including the specular effect, but what I really want is to add the roughness. Okay. This plus roughness, no, this plus roughness along these strips that you see over here makes it look much, much more realistic. Right? How did I introduce these strips over here? By saying that there is some height involved. Right? Same goes here. I start with this map, changing of height, plus description of a sphere. For hidden surfaces removal, this is just a sphere. Triangles that occlude it, some points you see the sphere, some points you don't see the sphere, but there are only two geometric primitives here. this triangle, and the sphere over here. Once you decide that the ray that you shoot is hitting the sphere, or that's the nearest point in terms of depth, the buffer calculation, then you start to wonder what the normal is at this point, and based on this normal, what the shading at this fact. My test is extremely cool. Right? So let's go a bit further. Let's go to relief map. What's the problem with only the normals? That if I ignore internal hidden surface depth removal, hidden surface removal, that's not a big deal. If I'm watching this part, this is my eye, and I'm moving my eye from here to here, there is not so much that is changing in terms of these surfaces. If I'll just change the illumination or change the reflection of each one of these surfaces, moving from here to here will not have a huge impact. When do I start to notice that I'm cheating with just a bump map? When I'm getting close to this surface. When I'm getting closer to this surface, suddenly this bump is supposed to hide, to occlude the next bump along it. Examples? I can get away from keeping on the other way. The bricks that are very close to the camera, you start to notice that it really matters which part of the brick you see. And just to make sure, it's still all the sidewalk here is just one triangle, one quad. That's all one planar object that you see as a quad for every depth. But if I will occlude the fact that these sub-bricks can occlude each other, the ones that are very close to the eye, very close to the viewer, that's quite noticeable that this brick occludes part of this brick, and if I move a bit, the part of the occlusion will change by a lot. So what? Does it mean that I really did 3D structure of the surface? Yes and no, depending to what purposes. To ask if I see the sidewalk or I see something that is behind it, I still treat it as a planar object. It's still one triangle or one quad. But once a ray comes from the eye, ray tracing or depth doesn't matter, Z buffer or ray tracing doesn't matter. A ray comes from the eye, I first compute where does it hit the tangent plane to the surface. I first think about a tangent plane that is where I think that the sidewalk is, maybe a bit higher than the sidewalk, and that's where I'll decide that I start my search for. And so I get my starting point, and now I go to the surface, and now I'm using the fact that it's not really, its normal plane will not do the job for me. What I need is a relief plane, relief map, that will tell me what is a Z value, what is a height, the height of every point, or this distance d, between the tangent plane, by how much should I deform it? Move a bit down, move a bit up. Deform it by a little over here, deform it by a lot right here. I can obtain from it the normals, obviously. It includes the information about the normals, but it includes more. It includes information about now once a ray hits the tangent plane that is very, very close to the surface. Once again, going back to the example. Once I decided that a ray hits the plane that is like a glass that is lying on top of the sidewalk, I start to ask which of the bricks does it actually hit. And that's a very fast calculation, sequential, nevertheless, but that's a very fast calculation. I'll start searching from here, find the corresponding teeth, and ask, now I'm walking along the ray, and at the same time, like merge sort, going along these teeth and along the ray in the direction of the ray, until finally I find the first object that this ray hits. Maybe it's this bump, maybe it's the next one, maybe it's the next one. But when they are competing about occlusions, other objects that are not the sidewalks are not in the game. I already decided that whomever the answer will be, it's from the sidewalk. And to get the answer about, hey, array, do you hit the sidewalk or not, it's just a simple Z buffer, or simple treat it as one triangle. This competition between the different maps starts only for the pixels that are suspiciously sensitive, that is, only the bricks that are very close to the camera. Once again, these bricks, probably bricks that are further away from the camera, probably you can avoid this game. The suspicious bricks are just the ones from the rays that are really near the camera, and only in case that small changes about your location, the player location, crunch bit changing by direction should generate different occlusions. This bump will occlude this bump, but there are only a few bumps that are suspicious. So even though it's linear and very, it's not a parallel process per array, sequential still goes very fast. Yeah?
Does that mean that relief mapping cannot be done using vertex and fragment shaders?
Well, fragment shaders move long way, since all they need to do is to compute depth. So the quick answer, depending on which normal shader, but I assume everything, since the moment that you could have actually run programs on each pixel, sure, it can be done. But it's not a constant amount of work per triangle. I still need to go sequentially from where the ray hits to, hey, do I hit the first bump? Or did I hit the next one? Do I hit the next one? And supposedly you can need to add some stopping condition, or else your ray can hang out long way. So sure, it can be done by the fragment processing, but it's still sequential operation. More examples of why to use normal map. 4 million triangles. A team from Stanford went to Italy to laser scan in enormous resolution all the Michelangelo statues. So I think that that's from there. Extremely specific, very three-dimensional, very small details. The stretches and chisels of the surface are very detailed. That's why it needed such an intensive scan. And you can still see it quite impressively, even though it only generated using 500 triangles. Make sense? Because each one of the triangles is associated with an image of normal map that was created from the original 3D statue. So once again, what is the process that you see summarized here? We started from, or they started, to be honest, from the, but hey, I was at Stanford, from the 4 million triangles that captured all the triangular, all the small details of the 3D structure, from which I created the normal at each point. And at this point, I don't use tiling. There is no tiling involved, but it does become just a pixel in a much smaller geometric shape. But and it looks good not only from one particular image, but it looks good as a 3D structure. Make sense? If I'll change my location with respect to this image, put it in computer game, I'll change my location, the whole image will change. Right? I'll change my location of light. Every pixel will change its shading depending on the location of the light. And also, some pieces of the statue occludes other pieces of the statue. Well, the nose might occlude some pieces over here, but that captures in the high level description. Okay, here's another example of environmental map. I'm into another application. In an environmental map, there is, you see big hole, its reflection on the ball. I can use the cube around me, or I can use a spherical map around me. There are pros and cons for each direction. I showed you beforehand how to use 6 images around you. Here we are using only one single image spherically around you with all the deformation. But now we can do ask for every pixel, which I do in parallel, or is done in parallel, to shoot a ray into the Stanford teapot. And from the shooting this ray, this pixel will have to decide, like you'll do in homework 6, will have to decide, oh, what is my color? I'll have to go to the environmental map to see if this was a mirror, how does the room reflect in the teapot? How to see the details, but you see the reflection of the room map into the teapot. How? For every pixel independently, I took this pixel and shoot a ray correspondingly to find its location, but that's just a single lookup per pixel. Single lookup per pixel, but it's not linear transformation in any way. It depending by what are the geometric primitives that I need. I need one image of the whole, one image of the whole, one description of the teapot, the normals of the teapot, smoothed. And now for every such pixel, it's a single lookup that is determined by the location of the teapot and location of the map. Okay, just because I'm mentioning homography multiple times, that's a process that you hear about it probably more in computer vision, less so in the context of graphics, but it's the same type of homography. I have a surface that is planar. Let's even make it a rectangle with 90 degrees, well-behaved rectangle. And when I have my camera watching and it's normal to the surface, hits the middle of the mirror, if you wish, how will it be seen on the image under this very specific condition? On the image itself, it would look like a rectangle, equal 90 degrees, equal rectangle. If I'll change the image plane to look at it from the side, it will stop looking in the image like the rectangle. Instead, the edge that is closer to me, will be longer than the edge that is further away. Instead of looking at the image just in front, now I'm looking at the image right here. So now on my paper, it will look like this. Still, these two guys are still parallel. These two edges stopped being. And if I'll move the camera to be even above it, then there is nothing 90 degrees anymore. However, it's still a linear transformation, affine transformation in homogeneous coordinates. Linear transformation, you're multiplying one matrix, or you're mapping 3 vertices, one triangle, three vertices of the image into 3 vertices at the output. Either case, you'll get it done for you. The homography happens automatically. But I want to mention the homography because it will help us in our next topic. Just have to start the very beginning, image-based rendering. So Wolf is a pretty complicated thing. It has lots of hair involved in details. And it might be even moving, which means that it includes parts in the background. I might be moving, the wolf might be moving. I still want to render the wolf as a 2-dimensional image. Now, as a 2-dimensional image, there are a few problems that I want to, or rectangle that is going to be mapped. into this image. There are a few problems that I want to solve. And again, think about it as an interactive game. First, the wolf is not a rectangle. The pixels that are not a wolf, you see the background. How do you do it? By assigning alpha equals 0 for all the pixels that are not on the wolf itself, right? That's, you know how to do. Everything that is not on the wolf itself, even though, so where are we going to? We are going to prepare in the pre-processing stage an image of the wolf, put it as a billboard in poser of the wolf. When I know where the viewer wants, that's why you have alpha. The camera moves a bit. Does the wolf change or does it not change? It changes, but in a very predictable way. If you just move the bit, then you just change the homography by a bit. Right? The side of the wolf closer to you becomes a bit larger than side outside, but it's still within the limits of 2D transformation, the homography. It happens without you noticing because it's linear transformation, vertices to vertices. That's for small changes of the location of the viewer. Where do I see that I start cheating? Why one image of the wolf is not enough? Because of self-occlusion. If I move a bit, one leg, one of the front leg will hide the other front leg. There must be some case that I cannot cheat, no matter how much homography trick I'll do. I cannot get one leg to occlude the other leg. Solution: don't prepare a single image of the wolf, but prepare a small number of the wolf from the multiple directions. And once you know where the user is, you can either decide, pick one of the 2D image of the wolf if the wolf is far enough and you're not planning to move a lot. And if the wolf is close enough that none of these images will do, at this point you need a better model of the wolf that takes the wolf as a 3D object. It's not always 2D. Right? So far away, one of a few directions will do. Close to the wolf a few separate images, which bring us to our next topic, that will say that sometimes I want to take an object and break it into multiple, not one image, but multiple images that I'll put one after the other and decided which image I'll use and which homography I'll do next, but that's the only reasonable way to render a very, very complicated object. You're pre-processing it, making a series of a small library of images. Each one is 2D image. And once time is due, use one of the images, put it, apply the homography that is just make the vertices properly, and you're done. Yeah?
For the slide like this, when you have the two different images, you do like different levels of detail?
By all means, I'll break the tree into multiple trees in the background. I care for this tree occludes other tree and self-occlusion of the tree itself, but I can get away with some level of cheating as long as I don't move. And I can also replace one image by another without too much notice. I don't need to replace the whole image by the whole image. So how come there is multiple images that you see over here? There is not one billboard. There are 5 billboards of different depths of the tree. How come they are all live together? Well, because each one, only the pixels of the bark of the tree are playing a role, and the other piece of the no tree are transparent. That's how there are multiple images, small but multiple numbers, and you let the graphic cards do the hard job for you of deciding what is occluded and what is not. People? Okay. Continue Thursday. Thank you.